If you're a developer who can code and ship features or fix some bugs here and there, but you can't explain how to scale things, how to increase the reliability of a system, or how to increase its availability, what are SLOs, then you probably will stay in the mid-level position, the best case scenario. If you want to get past that and get to senior roles and salaries, then you need to learn the foundations of system design, like how to design features or systems from scratch. And that's what we will cover in this video. We'll start from a single server setup and then eventually we'll scale it into multiple replicas, add databases, vertical versus horizontal scaling, load balancers, health checks, single points of failure, and much more. If you're currently stuck at junior to mid levels, then this is the knowledge that with enough practice will help you to get to senior roles and salaries. Designing a system to support millions of users is challenging, but every complex system starts with something simple. That's why in this lesson we'll build a basic setup that supports just one single user, and then we'll gradually expand it as we go. Because starting small allows us to understand each core component before adding more complexity. So let's start with the first step and build a single server setup. Imagine that we're setting up a system for a small user base. This means that everything runs on one single server. The web application, the database, the cache, and also the other components. And this setup allows us to visualize the core workings without added complexity. Now let's break down how this single server setup handles the user requests. We have some users who are trying to access our website or our API on the server. They can be either using the web browser or a mobile app to access our server. And on the other hand, we have our server, which has the necessary files to serve to the web browsers and also the necessary API endpoints to serve to the mobile app. And it is hosted on this example IP address. Initially, our users don't have this IP address. They have the domain which they are trying to access. Let's say it's app.demo.com. So if they just type this domain name and hit enter, their web browser, for example, will contact the DNS, which stands for Domain Name System. This is a provider which maps the domains to the IP addresses. And in our case, let's say our domain name is mapped to the IP address, which is the server's IP address that we have. So now this DNS provider will send the IP address back to the web browser or to the mobile app to our clients. And this IP address is our server's IP address, so now they have the location where they are trying to send requests. So with this IP address in hand, the user's device sends an HTTP request to our server asking for specific data. And then our server processes this request and sends back the requested data. This might be an HTML page for a browser or a JSON response for the app, depending on the request type. In this setup, traffic usually originates from two main sources. The first one is the web applications, and the second one is the mobile applications that are trying to access our server. For our web users, the server handles the business logic, data storage, and also presentation using HTML, CSS, and JavaScript. And for mobile users, communication typically happens over HTTP. These mobile apps request data from the server using API calls, and JSON is often used for responses because it's lightweight and easy for mobile devices to interpret. Here is an example API request that we can receive for our server. It can be a GET request to our domain /product/ the ID of that product. And for this endpoint, we need to retrieve the details of a product. And here is an example response that we might send back to the client. This is a JSON response which contains the product ID. It contains the name of this product, some description, the price of the product, and some other metadata that is useful for the client. And then this will be used by the mobile app or by the web browser to display this product on the screen. And as we continue, our goal will be to identify areas where a single server might not be enough for the user demand. For now, this setup is ideal for small user bases, but it may struggle under heavy traffic. So next we'll explore ways to scale each part of the system to support more users effectively. Some key takeaways that we can have from this is that we need to start small. We need to begin with a straightforward single server setup to understand the essential components of system architecture. Now we also understand how these requests flow through your system, which is fundamental for building more scalable systems. And we also recognize the unique demands for web and mobile applications and how they interact with your server. And in the next lessons, we'll start looking at strategies for optimizing and scaling this setup. Knowing this at a high level won't get you too far. If watching this course alone made you senior, then you'd be there with thousands of others who are watching this course. But in reality, not even 1% of developers get there from videos or courses. They get there by implementing with feedback and enough practice. And I keep seeing your comments, you want to learn how to implement these so that you can crush interviews or break past from the mid-level positions, and that's exactly what we do in my mentorship program. If you're a developer with 1 to 5 years of commercial experience based in US, Canada, Europe, Australia, or New Zealand, and you're stuck in junior to mid-level roles, but you'd like to move into senior positions, master system design, and start earning senior level salaries, then you can apply to work with me one-on-one. The first link in the description is where you can apply. This is exactly what I help developers do. We take these concepts that you see on the tutorials and apply them hands-on in real production projects with all the best practices, all the latest edge technologies. So basically the same way that senior engineers work in a team environment in top companies. Now it's time to practice, and in this first exercise we'll set up a single server on a remote hosting. I know that most of you want this to be with hands-on projects and assignments based on your responses, so we'll keep this as practical as possible. So as a first step, we'll set up a single server that can handle the web browser requests and also the API calls from the mobile app. To get started, I prepared this user management system application for you, which is a demo application that you can clone from this GitHub repository. Once you clone it, open in your code editor and let's look what we have inside. It's a very simple Node.js application with just two dependencies, Express.js and course. And we have a single start command which will start this server, and it will serve the static files and also the API endpoints. The starting point of this server is the server.js, so let's go inside of the server.js. Here we initialize an Express application, we set up the port and the host. We have some middlewares here, we enable the course. We use the Express.json middleware, and we also use the static middleware, which will allow us to serve static files from this public directory. Next, we have the CRUD API routes. We have the API/users, which will get the all users, and it will send it to the mobile app or the web application, depending which app will request for this. We can also request for a single user. We can post a user to save it to the database. We can edit the user profile by accessing /users/ID of that user. And we can also delete users by accessing the same endpoint but with a delete method. And apart from this, we also serve the HTML page, which is a static page that is located inside of the public directory, and it's called index.html. And after that, we start our app and we listen on the port and on the host that was provided above. So let's see what we have in the public directory. We have this index.html file, which will start the user management system. And it basically provides the same information that we have in these API routes, but it provides it with a user interface. And for now, the data is located in this mockdata.js file. Obviously, this is not ideal. Ideally, we want this to be stored in the database, but we'll look at that at a later sections. Right now, we are just using an array of objects to store these users in a JS file. As a first step, let's see if this works locally, and after that, we'll deploy this to a remote server. So you need to run two commands to start this server. First, you need to npm install with npm i. This will install the dependencies. And after that, you can run npm start. And this will start the server on the port 3000. If we copy this URL and open in the web browser, you can see that at the root we serve the static HTML content, which is this user management system. So we have our free users, which were defined in the JS file. We can delete them if we want, and we can also add users. Let's say this is a user with role user. We can click add and it will be added here. And we also have some basic validation, so it doesn't let you add if you didn't provide the details. Now let's see how we can access this with the API endpoints and not with the static content. For example, we can access the /API/users route. Let's try that in the browser. If you go to the same URL but /API/users, you will see the response from the server, which sends the user data. Here we fetch all of the users that we have stored in the database. And as you saw, we can also fetch a single user by accessing /users/the ID of that user. Let's say we want to fetch only these users, so the ID of this user is free. If you type /free after the endpoint and hit enter, Now you will fetch only the single user, and similarly you can access all of these other endpoints that are defined here. Just in case of these ones, you need to do them with a Postman and not through the browser. Now as you can see, this is running on our local computer and not on the internet. And we want to deploy this API server to the internet and access it from there. For that, first we need to choose a provider. You have many providers that can be used for hosting your websites or your APIs on the internet. For example, you have the AWS services. You have the Microsoft Azure. You have the Google Cloud provider also, where you can host your servers. There is DigitalOcean, and there are many more examples that you can use. So you can use the one that you feel confident. And there are many other examples which you can use. Since in our case we are just hosting a single server without some extra features, we can use DigitalOcean, and it will also be free for you to follow along if you want to deploy this with me. So if you want to use this for free, I will put a referral code down below which you can use to sign up, and then you'll get $200 for free to use in the DigitalOcean. And otherwise, feel free to use the hosting provider of your choice. The first step is to sign in to DigitalOcean, and now we can create a new server, and the server is called as a droplet in DigitalOcean. So you need to choose create droplet. First you need to choose a region, and this needs to be the closest possible to your end users so that it's faster to load. Right now it doesn't really matter because we are just using a demo project. Next you need to choose the operating system, which can be Ubuntu, Debian, CentOS and other things. Ubuntu is one of the popular ones, and unless you need some specific features of other OSs, you should choose Ubuntu here. And next you need to choose the CPU options. This is like choosing the computer where you will host your service. So obviously computer with higher RAM and higher storage will cost more, but it will be more efficient. And on the other hand, if you choose the lowest tier, it will have less memory and less RAM, so it will be slower. Since this is a demo project, we can use the lowest tier, but be aware of this when selecting it for production applications. And next you need to set up the authentication method. So you can either use the login and password, which is not recommended and it's not the secure way to connect to your server. The other option is to set up an SSH key. I recommend you set up an SSH key here by clicking new SSH, and here you can follow along the steps on this right side and create your SSH key and link it here. In my case I have it connected here, so I don't need to set this up. And that's it. You can also set up the host name here if you want to set this to a custom host name. In our case I can rename this to be user management system and hit on create droplet. This will create your droplet here, and you can connect to it by going to the Access tab. Here, if you have set up the SSH keys, you can just click on Launch Droplet Console, and it will exchange the SSH keys and it will sign you into the server. Now we are inside of that server. So you can imagine that now we are inside of this computer and we need to set up our application here. And the only difference from our local computer is that we can only access this through the terminal. So we don't have the graphical user interface to access it. And we need to run our application and everything using the terminal. Since this is a new computer, you don't have the Node and Git installed on it. So we need to install those to be able to run our application. You can Google the command to install the NVM, or you can just use this command that I will provide in the description and hit enter. This will install the NVM for you, and now you can install Node using NVM, so you can install the version that you want. Next you need to run the source bashrc command to update the terminal, so that now it understands the NVM command, and now you can install the latest Node version or the latest stable version. In my case I will install the version 22 and hit enter. So with that you can see that we have the Node version 22 installed. Now we need to also install the Git with this command. And this asks you if you want to continue. You need to type yes and hit enter. And that's it for the installations. Now you can run the source command again to update the terminal so that it understands the Git command as well. Or you can just close and reopen the terminal so that it updates automatically. And next we need to clone this repository, just like how we did for the local setup. We need to copy the URL of this repository. And in the terminal, you need to type git clone and the repository URL and hit enter. This will clone the repository inside of this server, and you can verify that by typing the ls command, and this command just lists the available repositories that you have inside of this repository. And as you can see, we have the user management system demo, which is cloned inside of this server. And now we can navigate inside of that repository by using the cd command, and this follows by the repository name, which is user management system demo, and hit enter. So this is the equivalent of being in the terminal here locally, but instead now we are inside of the remote server. We need to follow the exact same steps that we did locally. First we need to do npm install to install the dependencies, and next we need to do npm start to start the service. And now this service is running on the remote server as well. And we can verify that by copying the IP address of this server and opening a new tab with that IP address, and then followed by the port, which is 3000, and hit enter. And with that you should see this same application running on the remote server on the port 3000, and you can see all of the user data that we have. And you can also submit new users, and you can delete this, and you can also access the same API endpoints that we had. For example, you can access /API/users, and this will return all of the user data that you currently have stored in this server. And that's the very basic setup that you can do, but you can also take some steps to make this more secure and reliable. First, you can install some process manager to keep your application always running, and even if this remote computer is restarted, it will always make sure that your application starts along with it. For example, you can npm install the pm2 process manager, so you can do pm2 at latest, which will install the latest version, and -g for installing this globally. And that installs this globally, so now instead of doing npm start to start your service, you can do pm2 start and the entry file that you have, which is server.js in our case, and hit enter. This will start your same service, but it will first do it in the background, and it will also automatically restart whenever your server crashes. And finally, you can do pm2 startup Ubuntu, and this will make sure that pm2 service starts with Ubuntu whenever you restart your server. And with that, you should be able to access the same user's endpoint, and you should also be able to access the static endpoint from the port 3000. Now there are some more steps that you can take to make sure your API is secure. For example, you can see that we are using HTTP and not HTTPS, and for that reason we are getting this not secure sign. And also generally you would get rid of this port 3000 in the real production application, so that whenever they visit just your domain, they will see this website. And you can also connect this to a real domain by purchasing a domain from Namecheap and then connecting it to your website, so that users will connect to your domain and not your IP address. But I don't want to overwhelm you with too much information at this point, so we will explore these security aspects in the later sections. For now, we have successfully set up this server on remote hosting, and the users from the web browser can make HTTP requests to our server and get back the static content. And also the users from mobile app can use our API endpoints and get back the JSON format to display it on their mobile phones. As our user base grows, a single server isn't enough to handle the increased demand, and to accommodate more users, we can separate our web tier, which is handling the web and mobile traffic, and the data tier, which is managing the database. This setup enables us to scale each server based on its specific load. But when it comes to choosing the right database, how do we know which specific database is the best for our specific application? When it comes to database selection, there are two main options. The first option is relational databases, or RDBMs, which are structured in tables and rows. Some popular examples are PostgreSQL, MySQL, Oracle Database, or SQLite. On the other hand, we have non-relational or NoSQL databases. These are suited for applications that require flexibility and fast access to large volumes of unstructured data. Some examples are Cassandra, MongoDB, Redis, or Neo4j. Let's start by exploring the relational databases. These databases use structured query language or SQL for finding and manipulating data. The data here is structured in tables, which are the fundamental building blocks of SQL databases. And these are similar to spreadsheets. Each table consists of columns, which can be thought as the fields or attributes of the table. And it also consists of rows, which are single records within this table. For example, if you imagine a customers table, within this table we can have columns like ID, name, age, and email. And for each rows we can have specific customers like the ID of 1, 2, 3, and the name will be John and the age will be 30 and so on. But what are the advantages of using an SQL database? First of all, they support complex join operations across multiple tables. For example, if you imagine we have a customers table and also a products table, and now we want to create a separate table that will connect the customers and the products that they have ordered. With SQL, you can join these two tables together into an orders table, and this will hold the information about the customer IDs who have this order and also the product IDs which this customer has ordered. And this process of combining two or more tables into one table are called join operations in SQL. And the other big advantage is they provide robust data consistency and integrity, especially for transactions. Transactions in SQL are a sequence of one or more SQL operations that are performed as a single atomic unit, and each transaction in SQL follows the ACID acronym. You can think of a transaction example like a bank transfer. So first of all of the transactions are atomic, which means that the entire transaction is treated as a single unit, which either completely succeeds or completely fails. Each transaction is also consistent, which means that it transfers the database from one valid state to another valid state. And they also come with isolation, which means that modifications made by concurrent transactions are isolated from one another and they don't interfere with each other. And lastly, they come with durability, which means even if the system fails or the database server fails, the data will still remain there. And now let's have a look at non-relational databases. Non-relational databases can be in different forms. For example, we have document stores like MongoDB, or you can use wide column stores like Cassandra, key value stores like Redis, and graph stores like Neo4j. Let's have a look at each of these types separately, and let's start with the document stores. MongoDB is the most popular example of a document store, and the data here is stored in JSON-like documents, which allows us to have complex data structures within a single record. Next, we have wide column stores where data is stored in tables, rows, and dynamic columns. Some examples here are Cassandra or Cosmos DB. The main advantage of these databases is they can handle massive scales and are very good for many write operations. The other option is graph databases, which focus on storing the entities and their relationships as graphs. An example of a graph database is Neo4j. For example, in Amazon, they use the Neptune graph database, which helps them to make you product recommendations based on your previous orders. And the other popular type is key value stores. Here, data is stored in key value pairs. The biggest advantage of key value stores is their simplicity and speed. Since they are primarily stored in RAM, reading and writing to these databases is extremely fast compared to other databases. Some examples of key value stores are Memcache or Redis. So that's the main four types of NoSQL databases. Now let's have a look at the advantages of these NoSQL databases. If you have a look at the same example that we had for the SQL databases, where we have customers and products and we want to join them in orders. For example, in MongoDB, you could have this as a single document, so you could store all of the user data, also the orders and products in a single document. And because of this structure, the NoSQL databases can handle highly dynamic and large data sets without the structure imposed by relational databases. And also, they are optimized for low latency and scalability. So when should you use relational versus non-relational databases? Here is a quick comparison of both. If your application data is well structured with clear relationships, then you should use SQL databases. For example, if you have an e-commerce application tracking customers and orders, that's a good use case of using an SQL database. Next, if you need strong consistency and transactional integrity, for example, if you have a financial application or banking system, then you should use the SQL databases. However, if your app demands super low latency for quick responses, then you should go with non-relational databases. Or if the data is unstructured or semi-structured, like JSON objects, and the relationships aren't that crucial, then you should also go with NoSQL databases. And lastly, if your application requires flexible and scalable storage for massive data volumes, for example, a recommendation engine storing user activity data and key value format, then you should also go with NoSQL databases. Let's explore the two primary approaches to scaling, which are vertical and horizontal ways of scaling. And we'll also see why horizontal scaling is generally more suitable for high traffic applications. First, we have the vertical scaling, or sometimes it's also called scale up. This just means that we are adding more resources to our existing server, meaning RAM, CPU, or any other resources that might help us to handle more traffic. And this approach is simple and works well for applications that have low or moderate traffic. However, it comes with its limitations, which are firstly resource limits. There is a hard cap on how much you can add to a single server. And eventually you will reach a limit on how much you can upgrade your new server. And the second reason is lack of redundancy, meaning if this server goes down, you don't have any other servers to serve your users, which means that your whole application goes down with your single server. On the other hand, we have horizontal scaling, which is also sometimes called scale out. In case of horizontal scaling, we are just adding more servers to share the load. So instead of having the single server, we might replicate and have 3 of that same server. And now we can share that load between these servers instead of handling all of them in a single server. Generally, this is more suitable for large-scale applications as it comes with higher fault tolerance. And higher fault tolerance means if one of our servers goes down, we still have 2 servers available, so these 2 servers can continue serving our users while the second server recovers from the failure. And it also comes with better scalability, because you can just add more servers as needed. Instead of having 3, you might introduce a 4th one, which will handle the new incoming traffic. But how do we implement the horizontal scaling? In case of a single server, we know that all of our client requests went to the single server, whether it's from mobile app or from the desktop. But what if now we have 3 servers to handle all the load? How do we distribute the client requests? Let's say our mobile app makes a request. How do we know where this request should go? Whether it should go to the server 1 or server 2 or to server 3? And seems like we need to have something in the middle, which will direct the traffic to the appropriate servers. And that part in the middle is called a load balancer. We use load balancers to distribute the traffic across multiple servers. For example, here we have 3 servers, server 1, 2, and 3. Whenever we have a new request from the clients, the load balancer decides where we have the least load, and then it redirects the traffic to that server. And it also controls the fault tolerance, meaning if one of our server goes down, like the server 3, it will stop sending traffic to the third server since it's not available anymore, and it will send all of the traffic to server 2 and 1 until the server 3 is available again. And it also can make our app more scalable, because we can introduce a new 4th server and any other servers that we want, and this load balancer will ensure that all of the traffic is distributed evenly. So that's the 2 main approaches of scaling, which are vertical and horizontal ways of scaling. In case of vertical scaling, we are just adding more resources to our same server. But in case of horizontal scaling, we are adding more users to our server base. And then we use a load balancer, which distributes the traffic across multiple servers. But right now, this load balancer is kind of a black box for us, because we don't understand how does it work, how does it take the requests, and how does it distribute the traffic. So let's explore that in the next lesson, and let's see how this exactly works and what are the strategies that we use in load balancing. Knowing this at a high level won't get you too far. If watching this course alone made you senior, then you'd be there with thousands of others who are watching this course. But in reality, not even 1% of developers get there from videos or courses. They get there by implementing with feedback and enough practice. And I keep seeing your comments, you want to learn how to implement these so that you can crush interviews or break past from the mid-level positions. And that's exactly what we do in my mentorship program. If you're a developer with 1 to 5 years of commercial experience based in US, Canada, Europe, Australia, or New Zealand, and you're stuck in junior to mid-level roles, but you'd like to move into senior positions, master system design, and start earning senior level salaries, then you can apply to work with me one-on-one. The first link in the description is where you can apply. This is exactly what I help developers do. We take these concepts that you see on the tutorials and apply them hands-on in real production projects with all the best practices, all the latest edge technologies. So basically the same way that senior engineers work in a team environment in top companies. Load balancers distribute the incoming traffic across multiple servers while also ensuring that no single server bears too much load. But how does it actually happen, and how does the logic work of distributing the incoming traffic? To understand load balancers better, let's explore 7 strategies and algorithms that are commonly used in load balancing. Let's start with round robin, which is one of the most popular algorithms. That's mainly because it's the simplest form of load balancing, where each server in the pool gets a request in sequential rotating order, which basically means that the first request that it receives, it directs it to the first server, and the next request will go to the second server, and the third one will go to the third server. And once the last server is reached, in this case it's the server 3, it redirects it back to the first server, and then again to the second server, and so on. This works well for servers with similar specifications, meaning if all of our 3 servers have the same capability, then round robin will be a good choice here. Next option is the least connections algorithm. It directs traffic to the server with the fewest active connections. For example, if we have 10 active connections on the server 1, we have 9 active connections on the server 2, and we have 30 active connections on the server 3. If it receives a new request from the client, it will direct it to the server 2 because it has the least active connections at the moment, so now it will have one more connection. And this is particularly useful for applications where you have sessions of variable lengths, meaning that one of your sessions might last 10 minutes, the other one might last 1 minute, and so on. And in this case, the load balancer will take that into account and it will send the traffic to the least connection server. The third option is least response time. This algorithm is more focused on responsiveness of the servers. Let's say your first server is highly responsive, the second one is low responsiveness, and the third one is medium responsiveness. In that case, the load balancer chooses the lowest response time and with the fewest active connections, meaning first it will try to send as many connections to the high responsive server as possible. But it also takes into account the active connections. Let's say this server reaches 30 active connections. Then it will switch to the third server because this is the medium responsiveness server. And it will send some traffic, let's say 20 other requests to the medium responsiveness server. And after that it will switch to the second server and it might send another 10 requests to this third server until it redirects them back to the first server. This is effective when the goal is to provide the fastest response time to requests and you also have different servers with different capabilities. The fourth option is the IP hash algorithm, which determines which server receives the request based on the hash of the client's IP address. This is useful when you want your clients to consistently connect to the same server. Let's say client 1 makes a request to your load balancer. The load balancer will use the client's IP address and based on this it will hash it and send it to appropriate server, let's say server 2. And all of the future requests of the client 1 will go to the load balancer and it will use the same IP hashing algorithm and based on this IP address it will again redirect the user 1 requests to the server 2. This is useful if it's important for a client to consistently connect to the same application. If every of your server has some information about the clients that are connected to it, in that case the IP hashing is a good choice. Then there are also weighted algorithms. These are variants of the above methods that can be also weighted. For example, you can have a weighted round robin or weighted least connections. In this case, servers are assigned 2 weights, typically based on their capacity and performance metrics. For example, if the first server has 16 gigs of RAM, the second one has 32, and the third one has 64. Based on the server RAM and other metrics, they are assigned 2 weights. And the load balancer takes that into account when redirecting the traffic. First, it will try to send as many connections to the third server as possible, because it's more weighted, meaning it has more performance. And then it will try to send the other traffic to server 2. And then the last and small portion will go to server 1. There are also geographical algorithms, which are location-based algorithms that direct requests to the server geographically closest to the user. Let's say this application is for US users, so mostly users are connecting to this application from US. But we also have some part of the users who are connecting from Europe. And in our pool of servers, we can have one server that is located in US East, another server that is located in US West, and the last server can be located somewhere in Europe for the small base of users who are located in Europe. So if a user comes from Europe and makes a request to this load balancer, it will redirect this user to the server in Europe. Or if a user comes from the US and makes a request to this load balancer, it will check the location of this US user based on its IP address, and then it will redirect either to the US East or US West. This type of load balancing is useful for global services where latency reduction is important. And the last most popular type is consistent hashing. In this case, we use a hash function to distribute data across various nodes. We have a hash function inside of a load balancer, and we usually imagine a hash space along with this that forms a hash ring, like a circle. This hash function forms a circle where we have the servers, for example the server 1, 2 and 3, which are located in front of this load balancer. So whenever a new request comes from a user, this hash function takes the IP address of that user, and then based on that it locates this user on this hash ring. Let's say it locates it somewhere here. And then depending to which server this point is closest to, for example in this case this is closer to server 2, it redirects the traffic to that server. This is a bit more complicated way of load balancing, but it also ensures that the same client consistently connects to the same server, like in case of IP hashing. We also talked about that whenever a server goes down, this load balancer ensures that traffic is not redirected to that server. But how does it know in the first place that this server is not available? For that, most load balancers come with health check features, which means that they are consistently monitoring the servers by sending a health check requests to all of these servers. And they have the information about which servers are online. Let's say the first 3 servers are available and which ones are offline, which means the 4th server which is offline. So whenever it detects a failure in the health check, it knows that this 4th server is not available anymore. And based on that information, if the next request comes from the client, it won't redirect them to the 4th server until the health check again succeeds and it knows that the 4th server is back online. And now let's see some load balancer examples and what are these actually, how do we implement them. First we have software load balancers. For example, Nginx is probably the most common type of the software load balancer. It has other features and it's also used as a web server, but it also offers the functionality of a load balancer. Typically you install this Nginx on your server and then configure the servers that should be load balanced and also the algorithm. And as you can see, it also comes with health checks, which I mentioned. So you can set up health checks among your servers, and then this will consistently monitor your servers, and whenever one of your server goes down, it won't redirect traffic to that server. Another example of a software load balancer is AJ Proxy, which is an open source software that again you can install on your server and configure as you want. But apart from software load balancers, we also have hardware load balancers. For example, we have the F5 load balancer, which is a widely used hardware load balancer known for its high performance and feature set. Next we have Citrix, which also comes with load balancing functionality, and again this is a hardware type of load balancer. But if you don't want to configure all of that yourself on your server or as a hardware, then the easier solutions are cloud-based load balancers. For example, AWS comes with elastic load balancing, and if you have your servers also set up in AWS, then it's pretty easy to configure this with your servers. And you can also see it in the benefits that it automatically comes with security, automatic scaling, meaning that it will automatically add new servers to the pool if the demand increases of your application. And it also comes with monitoring, which is the same as health checks, so you don't have to set it up yourself. And other examples similar to AWS are Azure's load balancer and Google Cloud's load balancing. Now let's talk about a concept which is called a single point of failure in system design. This is one part of your whole system that whenever it fails, it will bring the entire system down with it. So to put it simply, it is any component that could cause the whole system to fail whenever it stops working. For example, if you imagine this setup, when the clients connect to our load balancer and then load balancer distributes them to the APIs, and then we have a single database which is used for all API servers. Database here is one example of a single point of failure. Whenever this database goes down, all of these APIs won't be able to connect to the database, and because of that, all of these also won't function properly, and our clients won't be able to receive any response from the servers. So having single points of failures in your system is problematic because they can create vulnerabilities. The first obvious downside is the reliability, because a single failure, like the failure of this database, can take the entire system down, which could mean business losses because users are not able to access our platform. Maybe they are also not able to access the checkout page or any other parts of the system, which can bring losses in the business. It is also an issue for scalability, because systems that have single point of failures like this can often struggle to scale, as each component will add a risk of failing this single part. And the last part, it also brings a security issue, because if you have a single point of failure in your system, like the load balancer, attackers can compromise this point by sending huge traffic to it, and if this fails, the whole system will go down. We will talk about how to avoid the database single points of failure in the databases section, but in this section we can have a look at how to avoid the load balancers to become a single point of failure, because right now we have only one load balancer set up, and if this load balancer goes down, then all of our users won't be able to access this point, and they will also not be able to access to our APIs. The first strategy is adding redundancy to our system. This means that we can use more than one load balancer, and for example, if the second load balancer goes down, users won't be able to connect to this load balancer. But in that case, we can redirect all of the traffic to the first one, and then this first load balancer will balance the load between those servers. And we will monitor the health of this second load balancer, and whenever it's back online and it's again available, we will also redirect 50% of the traffic to this second load balancer. Another strategy is to use health checks and monitoring for load balancers themselves. As we saw, load balancer can do health checks for the servers and check whenever our servers are online or offline. We can do the same strategy for load balancers, and we can check their health continuously, and whenever one of our load balancer goes down, we will know that we shouldn't redirect any traffic to this load balancer until it is back online. And the third common type is self-healing systems, which means that we again monitor the health of our load balancer, and if at any point we detect that it goes down, we will replace this with a new load balancer, which is basically an instance of this same load balancer, and this way we won't cause any interruptions and our clients will be able to connect to this new load balancer. And in the next lesson, we are actually going to implement our own load balancer, and there we will also implement this first strategy, which is redundancy. So we will set up two load balancers, which will be responsible for handling the clients, and this way we will avoid having single points of failure in our system. Now we get to the fun part, which is actually implementing a load balancer. In this exercise, we are going to set up a load balancer with multiple API servers on DigitalOcean. This will help us to distribute the incoming traffic across multiple servers, which will improve the reliability, and we will also prevent having a single point of failure by setting up two load balancers for redundancy. This was just the first section of the full system design mastery course. If you'd like to continue watching and learn all the other necessary concepts to get you to senior role, and also see live implementations and implement them hands-on on real production services, then you can apply to work with me one-on-one in the mentorship program. The rest of this is exclusively for the people who are in the mentorship program.